Welcome to part 4 of Eigenvalues and Eigenvectors. So we have determined eigenvalues and eigenvectors, and we have in fact determined that for a specific eigenvalue there is a specific corresponding eigenvector. There is a vector that makes this equation, this is a column vector equation, makes that equation true. So we have found a value of lambda, and we have found a value of a vector, a column vector, in this case column v, for which f times v equals lambda v. So now it's time to verify our calculations, right? So this vector, column vector minus 1, 1, 2, is the column vector associated with the value of lambda, lambda equals 3. And what we would like to do is to verify this vector equation. So first, let's consider something. So remember, we're trying to verify that f times v equals lambda v. So we're going to work with the left-hand side of that vector equation, and means we multiply the matrix times that vector, and that's exactly what we consider here. First, this is a linear combination of the columns of the matrix with scalars. Scalar coefficients being the entries of that column vector, so minus 1, 1, and 2. And this becomes the addition of vectors 13, minus 12, minus 24, added with the second column stays exactly the same. Third column becomes, and this sum here, minus 8, 8, and 7. Excuse me, I have to make a correction here. So the last entry on this vector is the product of 2 times 14, which is, 2 times 7, which is 14, and not what I had previously written here. So the next step would involve adding up entries component-wise, entry by entry. So we have 13 minus 8 minus 8, and that gives us minus 3. Then we have minus 12 plus 7, that is minus 5, plus 8, that gives us 3. Then we have minus 24 plus 16, that's minus 8, plus 14, and that gives us 6. So as far as the left-hand side of that verification, by multiplying the matrix times the vector, we're obtaining that that equals this vector. Now we'll work with the other side. So what we would like is to multiply the vector times the scalar, which in this case the scalar is 3 and the vector is minus 1, 1, and 2. By doing this multiplication, we obtain the vector minus 3, 3, and 6. And so we observe that both of these things are exactly the same, and this is exactly the confirmation or verification that we needed to do. Right? So we have concluded that both of these things are exactly equal. In other words, we're concluding here that when multiplying the matrix times the vector minus 1, 1, 2, and multiplying the scalar times vector minus 1, 1, 2, they are, each of those multiplications, each of those products, each of those multiplications is equal to a vector, to a column vector, and in fact that concludes that both of those multiplications are equal to each other. So here we have the right hand side is 3 times that vector, the left hand side is the matrix minus 13, 12, 24 in the first column, second column minus 8, 7, 11, and then the last column is minus 4, 4, and 7. So we're concluding that indeed, right, FV equals lambda V, which is what we needed to, that we needed verification. Left-hand side equal to the right-hand side. So now we consider the other vector, the other eigenvector, and we're going to consider the value too associated with that eigenvector. So we're multiplying the matrix times the column vector minus 3, 3, and 3. So that means we have a linear combination of the columns of the matrix where the scalars in the linear combination are given by minus 3, 3, and 3. And this leads to 3 vectors. So we have the vectors, well, these 3 column vectors, each of them resulting by carrying out that scalar vector multiplication. And when we add up these 3 vectors, we end up 39 minus 24 minus 12 gives us 3, minus 36 plus 21 plus 12 is going to give us minus 3, and minus 72 plus 48 plus 21 will also give us minus 3. So the thing we have to now verify is that also, on the other hand, if we take the vector and multiply that vector by a scalar, we take the vector minus 3, 3, take the vector minus 3, 3, and 3, and multiply that by the scalar negative 1, then immediately we get 3 minus 3 minus 3, which is exactly what we had obtained by checking the matrix vector product. And so this leads to verification. Indeed, they match. They're both, each of those products, the matrix here, the matrix vector product equal to this column vector, and the scalar vector product, the scalar column vector product equals to this column vector, and both of those column vectors are equal to the same thing. So that matrix vector equals that scalar vector, and that is exactly what the definition of eigenvalues and eigenvectors is about, and we are simply verifying that this definition holds true precisely because we constructed the eigenvectors based on this definition. We computed the eigenvalues based on that definition. So the eigenvalue and eigenvector problem is eigenvalues and eigenvectors are very important in linear algebra. They're very important for matrices. Many applications rely on these so-called eigenvalues. But the calculation of eigenvalues and eigenvectors merit that we put in order here some type of recipe or algorithm, and I just want to emphasize that this is rather an advanced topic in our adventures of linear algebra, and gracefully, eigenvalues and eigenvectors is the kind of topic that requires heavy machinery of many of the tools that we have learned so far. This requires calculation of null space. This requires, and therefore for calculation of a basis of the null space, we have to rely on reduced row echelon form. This requires computation of the determinant of matrix, something that we haven't really learned in this class, but we certainly know from previous basic mathematics adventures, is the calculation of roots of a polynomial, specifically polynomials of degree 2, quadratic polynomials, and then polynomials of degree 3 when they can be factored out in a way in which that polynomial can be expressed as involving the multiplication of polynomial of degree 2. Then finding the roots will heavily rely on the so-called quadratic equation, right? So we compute eigenvalues based on calculation of the zeros or the roots of a polynomial called the characteristic polynomial, and then we have to do some evaluation, compute a new matrix, and compute the basis for the null space of that matrix to come up with eigenvectors associated to specific eigenvalues. So here's the summary of these steps that involve in the calculation of eigenvalues and eigenvectors. So we consider the eigenvalue problem being A times a vector V, non-trivial vector, and lambda times that same vector. Both of those things are equal to each other. Lambda is a scalar called eigenvalue, and V is a vector that has as many entries as the number of columns of the matrix A. To solve the eigenvalue problem, which is that vector equation, we'd like to follow these steps. Number one, compute the quantity a minus xi, and now compute the determinant of a minus xi. Remember, you could also think of this quantity as p sub a of t, and this would be the determinant of a minus ti, right? So this simply denotes what is the variable in the polynomial, right? We could write some other letter there, for example, p sub a of s, and so here we say determinant of a minus si, okay? So that simply is the letter that's being subtracted. And so first thing is we compute this characteristic polynomial, then, and this may be an involved step, we compute the roots, or the values at which this polynomial becomes 0, right? And so those values are typically defined as roots or zeros of the characteristic polynomial. We want those because those roots are going to be the so-called eigenvalues of the matrix A. Okay, even though the polynomial is based on the definition A minus the letter used for the polynomial, t, x, s, or even lambda, right? You're subtracting from the diagonal entries of A one term there, x or t, and then you compute the determinant of that. Then the calculation of the roots of those determinants is a significant step. In general, we're talking about a polynomial, here denoted as p sub a of x, of degree n, and a polynomial of degree n has always n roots. In other words, a characteristic polynomial always has the matrix A has always n eigenvalues, where n is the number of rows and columns of that matrix. And then what we do next is, well, we know that the n roots of the characteristic polynomials are n eigenvalues of A, which make the matrix A minus lambda I singular. So we would like to, in fact, use that last piece of information. We want to compute for each value of lambda, compute the matrix A minus lambda I, and then compute the basis for the null space of A minus lambda I, and an element of that an element of that null space is precisely the vector we call eigenvector, which is associated with that specific value of lambda. So here we leave as an exercise. I like you to pause this video lecture now, and do the calculation that involves computing, basically going over those 3 steps with this matrix here in number 1, and also with this other matrix in number 2.